Good morning, everybody. I'm Luca Vecchiato, PhD student at the University of Padua. First of all, I want to thank the scientific committee and the organizer to give me the opportunity to share with you my research. Today, we'll present a work on the application of the peak stress method for estimating the fatigue life of welded joints subjected to variable amplitude loading. The presentation is divided into four sections. The first one is a theoretical background on the peak stress method and on the equivalent peak stress concept, which represent an engineering application of the not stress intensity factor approach applied to fatigue failures of arc-welded steel joints in the as-welded condition. Later, it will be presented how variable amplitude loadings can be taken into account by simply combining this method with a cumulative damage rule, and in particular, a linear damage rule will be adopted. Afterward, in the third section, some data taken from the literature will be reanalyzed to check the validity of the proposed method against experimental data. Finally, the most important consideration will be recapped in the conclusions. Criteria based on local quantities are considered reliable methods for fatigue assessment of welded structures. According to the observation that the conventional arc welding techniques result in very small values of the weld toe radius, the worst case geometry is assumed for the weld toe and for the weld root. Such hypothesis consists in modeling them as sharp V-notch. Owing to this assumption, the external loads generate singular stress field at the weld toe and at the weld root. In the framework of linear elasticity, the not stress intensity factor quantifies the intensity of this asymptotic stress distribution and has been shown to be a fatigue-relevant parameter. The peak stress method is a numerical tool proposed by Meneghetti and Lazzarini in 2007 for a rapid estimation of this NCF by means of linear elastic finite element analysis with relative coarse meshes. The NCF can be computed thanks to the reported expression, in which KFE star is a calibrated constant. Sigma 1 peak is the nodal value of the opening peak stress evaluated at the P-notch tip. D is the average size of the finite element, and at last lambda is the stress singularity degree, which depends on the V-notch opening angle 2 alpha. Such method has the following advantages. Coarse meshes is required if compared to that required to apply the NCF definition. Just one nodal stress value is required instead of the whole stress distribution to compute the NCF. And moreover, the free mesh generation algorithm can be adopted to create the finite element model. At last, just some specific information about the calibrated constant KFE star. It depends on the element type and formulation, and also on the finite element mesh map pattern and on the deployed finite element code, in particular on the procedure adopted by the code to extrapolate stresses at nodes. It has been calibrated in ANSYS for the reported 2D and 3D element type, but this is not the only calibrated software. For more information, please refer to the reported reference. In the context of the NCF approach, Lazzarini and co-workers introduced a local approach for the fatigue strength assessment of no-shot components, which assumes that the average strain energy density evaluated in a circular sector of radius R0 and surrounding the correct initiation point is the fatigue damage parameter. This radius has been found to be equal to 0.28 mm in case of steel welded joints. It has also been shown that if high-order non-singular stress terms are negligible, it can be written as a function of the not stress intensity factor. Therefore, by adopting the PSM, it can be rewritten as a function of the relevant peak stresses. Moreover, by introducing the strain energy density value of an equivalent uniaxial plane strain state, the equivalent peak stress can be defined by the following expression. In this expression, CW1 accounts for the mean stress effect, while FW1 accounts for the stress averaging inside the material structural volume, which has a radius R0. The equivalent peak stress has been adopted as a fatigue damage parameter, and a master fatigue design scatter band was defined for arc-welded details made of structural steels and subjecting to prevailing Mod 1 under constant amplitude loadings. The aim of this work was trying to extend the formulation of peak stress method to take into account variable amplitude loadings. Trying to preserve as much as possible the simplicity of the method, it has been proposed to use them in conjunction with a linear cumulative damage rule. The proposed procedure is quite simple and can be divided in 4 steps. The first thing to do is to obtain the nominal stress range spectrum, for example by applying a cycle counting algorithm to a load time history. Then the welded detail had to be modeled adopting the assumption of sharp V-notch we have discussed before. At this point, it is necessary to create a finite element model of the welded detail according to the PESM and evaluate the nodal opening peak stress value at the V-notch tip. At this point, for each nominal stress range, it is possible to compute the equivalent peak stress range and obtain the stress spectrum in terms of equivalent peak stresses. Please note that for its evaluation, only one linear elastic finite element analysis is required or necessary. So the last step required the application of the linear damage rule. The number of cycles to failure for each applied stress can be computed from the PSM Mod 1 design curve we have seen before. Moreover, a constant slope K1 no cutoff limit has to be chosen. Finally, an equivalent constant amplitude peak stress can be obtained by equating its fatigue damage with the one of the spectrum. To check the validity of the proposed method, a large number of fatigue data taken from the European Steel Research Program cited below has been reanalyzed with the peak stress method. In this work were tested 2 different types of joint, a full penetration transverse no-load carrying attachment and a full penetration transverse flat weld. Both the joints were made of 2 different blade thickness, 10 mm and 30 mm. The 10 mm ones were actually loaded, while the thicker ones were subjected to 4-point bending loading. All joints were made of 4 different grades of steel and were tested in the as-welded condition for a total of 450 specimens. Tests were carried out both under constant and variable amplitude loadings. The variable amplitude loadings were conducted under 2 different spectra of a Gaussian type, but one of them with overloads. Both were applied in random order. All spectra were applied under fully reversed or under pulsating loading for a total of almost 236 and 214 fatigue data under constant amplitude and variable amplitude respectively. Now we will see an application of the proposed method. Starting from the whole specimen geometry, the information related to the real welded geometry were taken from the reported image. Then it was simplified and modeled according to the sharp V-notch assumption discussed before. Later, a plane finite element model was realized in ANSYS by adopting a plane strain for nodal linear quadrilateral elements. So it was possible to evaluate the nodal opening peak stress value at the V-notch tip and consequently compute the equivalent peak stress range for each applied nominal stress range. At last, by combining such result with the PSM Mod 1 design curve, it was possible to compute the equivalent peak stress range to be adopted as a damage parameter, also in case of variable amplitude loading. In this way, it was possible to reanalyze fatigue data for all specimen type and for all steel grades. Furthermore, each analysis was done for all the applied stress spectra, so both for constant amplitude loading and also for variable amplitude loading. The reported experimental value of cycled failure are related to complete failure of the welded joints, and in particular, crack initiations were found for all joints at the weld toe. It has to be noted that the scatter bands are not fitted on the experimental data, but for the case of the constant amplitude loading in the left figure, and also for the variable amplitude loading in the right figure. So, coming to the conclusion, the peak stress method has been reformulated to take into account variable amplitude loadings in the estimation of the fatigue lifetime of arc-welded steel joints subjected to prevailing mode 1 loadings. The goal was achieved by combining the peak stress method with a linear cumulative damage rule. The obtained design stress is a combination of the linear elastic peak stress, which can be obtained from finite element analysis, and the nominal stress range spectrum. The first advantage of adopting this procedure is the fact that the PSM can rapidly estimate the linear elastic peak stress, adopting linear elastic finite element analysis, which have rather coarse meshes that are generated from the free mesh generation algorithm present and available in all commercial finite element softwares. Moreover, being a linear elastic parameter, only just one finite element analysis is required for a fixed specimen geometry and loading mode. The capability and the validity of the proposed method was checked against a large number of experimental results taken from the literature, which were referred to steel joints having different geometries, made of different steel grades, and tested under different load spectra. At last, coming soon, in the near future, the method will also be extended for taking into account multi-action and variable amplitude loadings. So that's all, and I really want to thank you for your kind attention.